So let's now proceed with the vacuum electron devices simulation and how we can really handle this with the CST Studio Suite. So this is the outline of my talk. I will then introduce you first the context of use, a bit of history and device classification. Then we will proceed with the passive components and how we can also simulate this kind of devices. Then I will go to the active devices, show you the differences that we have between amplifiers and oscillators. And then I will go to the high power microwaves and I will show you some nice examples that we are able to perform. And then we'll go to the conclusion. So let's start with the context of use. I would like to start a little bit with a bit of history here and see the context where all these devices has been used and are still used also nowadays. So if you see from the first experimental discovery of the electron from Joseph John Thomson, and also with the discovery of X-rays at the end of the 19th century, then we've seen the development of the cathode ray tubes, which are mainly related to X-ray tubes and, for instance, electron guns, which are then also be developed at that time. With the first wireless transmission, which has been discovered by Guglielmo Marconi early in the 20th century, then we've seen the development of the so-called vacuum electron devices, where we can extract an output signal from an interaction between an electron beam within an RF structure. And you can see that mainly during World War II, we've seen the development and the tubes such as klystron, magnetrons, and traveling wave tubes, which has been developed, especially for radar systems and for the need in communication that we also had at that time. This constituted the active devices. And in the 70s, then you see that due to the technology, and especially the technologies related to the high power generators, then we were able to develop relativistic devices and so-called high power microwaves. This has been started in the 70s, and they are still developed nowadays as research activities and are still also study in the different areas and countries. About the classification of electron devices, we can distinguish, regarding the histories that we've seen previously, we can distinguish between the classical devices, conventional devices, and the relativistic devices. And then you see here the differences between both. The emission process. So for the classical devices, you start with a hot cathode, with a thermionic emission process, whereas with the relativistic devices, we are starting with an explosive emission and using cold cathodes, which can be made of velvet-coated cathodes and so on. The pulse duration for classical devices is much longer than the pulse durations that you have for relativistic devices, especially because then in this case you handle with plasma, with breakdown, which will also limit for relativistic devices the pulse durations. And this is something that we call also sometimes pulse shortening. The output power is limited for classical devices, which is roughly below 100 megawatt, whereas for relativistic devices, it can really be up to several gigawatt. And finally, the applications that we have behind. For the classical devices, this is related to embedded devices, such as industrial equipments, medical devices, space tubes, and so on. And for relativistic devices, these are mainly militaries and research activities. So let's start with the passive components. The first passive components that we can analyze and that we can have also in mind is the electron gun. And the the most simple electron gun that we can consider is the Pierce gun. So the Pierce gun is the one that you have here on the screen, and the particles are emitted with the child-Long emission, and you have here the equations for the emission of the particles in order to generate the maximum current, which is then here extracted and flowing into the structure. The space charge and the temperature can also be taken into account for the thermionic emission that we have here. And then in this case, this limits the maximum of current that we can extract out of the electron gun. And the space charge can also be taken into account. So as we explained already earlier, the space charge with the Coulombian effect, which is superimposed to the external fields that we have, which are also generated in the structures, are then superimposed in the device. And then you have an iterative process with a convergence analysis, which provides you with the maximum currents that you can extract out of the tube. It's a solid beam formation, and you have specific focusing electrodes. We don't need any external magnetic field to focus the beam in the area where the particles are emitted. And this, thanks to the Pierce cathode, everything has been set in order to extract a solid beam with a current which is then limited to 1 amp roughly. Regarding the electron gun, which considered cold cathodes, so cold cathodes, here you have different kinds of emission models which then can be used. It can be explosive or field emission, but it can also be a space charge limited emission when you consider also the high voltage. And then in this case, you can also superimpose the space charge. And then you have the figure that you have also here on the bottom left on this slide, where you can see also the space charge iterations in order to extract the maximum currents that you have here for this application. You see here as an example, you have an hollow beam formation. And for this, specifically because of the shape of the electrodes, then you need to apply a static B field along the tube axis in order to focus the beam. And here you can reach high current emissions of the type of several kiloamps, which then can be done here. Another applications of passive components are the X-ray tubes. And in the beginning, so as I said, early near the end of the 19th century, early in the 20th century, you had the development of the Crookes tube. The Crookes tubes are defined from a DC electrical discharge, where you have a ionization of the residual gas within the tube. So then you create the discharge, and then here you have some ions which are then created, and the ions are going to bombard the cathode. The cathode are going to emit secondary electron emission, and these electrons bombarding the anode structures can then generate some X-rays. So this is the type of tubes that we can fully dimension and we can fully design, and then we can also validate the prototype using the simulation. There have been some enhancement of the Crookes tubes. This is the Coolidge tube. So then we can replace the discharge that we have with an electron gun. So that means that in this case, you directly introduce into the device the electron beam, and then this electron beam is going to hit the target, and from the target, you will extract the X-rays. And modern tubes, like you could also see here as a picture here on this slide, you have slight modifications and realizations of issues which are then related to heat dissipation. So that's why you have some special tubes for that. And you also have the design of rotating anode tubes. This is the type of structures that you have here. And also you can also have cold cathode tubes based on field emission, which can also be used depending on the energy of the X-rays that you would like to have at the end. Typical components of X-ray tubes are the following. You have the emitter, which is typically the electron gun. Then the grid for the focusing electrons in order to have also a beam control, and the focusing systems which embed external electrostatic or magnetostatic fields if necessary to guide the particles to hit the target. The target is at the anode potential, which generates the X-rays, and the anodes that you have here are accelerating potentials and electrical conduction path in order to also to guide the current that you will which will flow also into the device. We can couple this to any thermal analysis in order also to analyze the heat dissipation. The enclosure, which is not shown here, as the vacuum vessel, the structural supports, and the electrical and X-ray screenings, is not drawn here on the slides. But of course, all the surroundings needs to be taken into account to get the whole analysis of the whole tube. Now, the typical outputs for the design of X-ray tubes are the following: the metrics of the beam, all the different parameters and analysis that you can extract from a tracking analysis. Then you have the total beam current, the beam current density, the beam trajectories, the space charge, and so on that you can analyze. You see here you can place a so-called particle 2D monitor, and then you can analyze the beam profile at some certain positions. And current and power deposition can also be analyzed as soon as the particles are hitting the target. Then you have primary and secondary particles, which then can be considered. And you can also calculate and do a multiphysics approach in order to compute also the increase of temperature that you have when the particles are hitting the target. And last but not least, something which is also very important for the efficiency of this tube is the surface erosion profiles, which then can also be computed. You can here analyze the target erosion profile. You have special post-processing for that. And the erosions, which changes also the device dimension. And then you can also analyze any damage effect. Let's now move on to the active devices. And I would like to start with the amplifiers. So the main famous amplifiers that we've seen already during this session is the traveling wave tube. How does that work? So you have an input RF signal, which is then introduced here into this coaxial structure. And then you have here a slow wave structure, which is made of these helical structures, which can then here maintain the RF signals propagating along the tube that then you can then extract here to the RF output. The particle beam, which is propagating into the RF structures, is there to allow a transfer of energy from the particle beam to the RF structures being amplified along the tube in order to extract the RF output power. This is exactly the opposite way of an accelerator, where you would have the fields which would be then transferred from the RF signals to the particles to accelerate the particles. So here there are key factors to take into account. You need, for the amplification process, to have a modulation of the electron velocity, which is the so-called bunching effect that you need to have of the particle beams into the slow wave structure. The slow wave structures is there to allow some synchronism conditions between the phase velocity, which are then propagating along the helical structures, with the electron velocity of the particle beam. And then at the end, part of the electron kinetic energy is transferred to RF. And the RF input amplification is computed here in the output. Keep in mind that the static B field that we have to apply in this condition is only this to focus and to maintain the electron beam along the tube axis, but the static B field doesn't contribute to the interaction process. So let's have a look to this example, and then you can see how powerful can be a CST studio, especially in terms of size, mesh cells, number of particles that we can take into account, especially for these particular examples. You have here a full klystron examples, which is 1.25 meter long, and then made of 7 cavities. By the way, this is a tube which have been studied in the past by one of my colleagues, Ulrich Becker, that you have here on the slide. And then this is something that we can really reproduce now in real 3D, taking into account the whole tube, which was not possible in the past. So you see here, you have a beam energy, which is 535 keV, an E-beam current of 700 amp, and an RF input signals at 3 gigahertz. The numerical settings here, you have roughly 4 million mesh cells, and the hex mesh refinements is performed up to 30 lines per wavelength. You see here that these 5 cavities that we have here constitutes the equivalent slow wave structures where we will have here bunching effect for the particles. We inject here the RF input signals, and here the RF input signals will then interact with the particles, which are then going to be bunched, and here we extract the output signals for the amplification process. We need to design also the klystron output coupler in order to extract the microwave signal out of this cavity. So here you see, you can start directly, whatever from a particle 2D monitor, or even from here, this small cylinder that you can place here in this area. Then you launch the particles using, for instance, a Gaussian emission, and then you apply the static B field in order to focus the electrons in the tube axis. And you see that as soon as the particles has transferred their energy to the cavity, to the output ports, then the particles are then unbunched, which is the signatures of the microwave signal, which is then extracted out of the device. You can also nicely see this from the E-field representations at 3 GHz. We can monitor here from the waveguide port the output signals, and then you see that a fast Fourier transform of this signal, or a discrete fast Fourier transform of these signals, provides you with the main response here that you have, which is then normally the amplification process at 3 GHz. Let's then analyze the results, and here the main amplification process. So the klystron input power is coming from the E-beam. Then we can compute and calculate here analytically the input power that we have in the tube, which corresponds to here 375 megawatt. And the klystron output power is directly computed from the signal, which is then recorded from the waveguide port, from the output waveguide port, which is located here. And then here you see that we have a total output power of 144 megawatt. We can then calculate the gain. You have here the output signals. You cannot clearly see the input signals, but the input signals is defined here in this equation. So we can calculate the gain, and we have here for the full device, then we have here a gain of 47 dB. If we do a fast Fourier transform of the signals, then you can nicely see that we have here an amplifications at 3 GHz. In terms of performance, that's impressive. And I think this is something which is really unique with CST Studio Suite. And you can see here that for roughly 4 million mesh cells with an average number of particles, which is 5E5 written here, with a maximum memory which is not that large, which is only 3.6 gigabyte of RAM, which is used, you have here the performance that we can really reach, the simulation times with the CPU, which is roughly 2 hours, whereas as soon as we are using the GPU, then we can compute these simulations within 16 minutes. So that means with the GPU approach, we can reach the speed up factor of nearly 8. That's really nice and really promising in terms of complexity that we can also handle with CST Studio Suite. Let's now move on to the oscillators and how it behaves. So the famous oscillators that we know now, despite of these presentations, but this is something which is also commonly studied also in the community, is the magnetron. So here the magnetron, as I said also previously, this is a cross-field device. That means that you have a perpendicular external magnetic field to the E-field components. So you have the cathode structure, you have the anode structure. The magnetic field is perpendicular to this screen, whereas the electric field is here radial to the in between the cathode and the anode structure. You need now to design the magnetron in a way where it exists a synchronism condition between the electron velocity and the phase velocity of the electromagnetic waves induced into the RF structure. And this is performed by the electron drift velocity. The electron drift velocity is computed with the electric field radial divided by the magnetic field along the z-axis, which needs to be equal to the phase velocity of the slow electromagnetic wave. And then the energy is transferred from the rotating e-beam to the slow electromagnetic waves. And exactly in the same way as for an amplifier, as soon as you have a bunching effect for the particles, which is the spokes formations that you have here within this magnetron, then in this case, you can emit a microwave radiation. And here, so remember what I said also for the amplifiers, the static B field participate to the interaction process because the static B field is embedded into the equations which computes the velocity. And the velocity of the particles is key to maintain the synchronism conditions with the phase velocity of the slow wave. So let's analyze real examples that we can also consider here in our tools. You have here an example of a 4 kilowatt magnetron, and you can also find it easily in the CST component library. You have a DC feeding voltage of 4.3 kilovolt, which is introduced in this area. And this can also be formed using the circuit simulation. You can introduce also your input signal directly from the circuit simulations, which will be connected to the 3D environment. And then you can do a particle in cell co-simulations with the circuit environment. So you introduce your high voltage from here, and then you emit the particles from the cathode, which is there, to the anode structures, which contains also these cavities. A static B field of 0.18 Tesla is applied along the tube axis, and depending on the type of magnetrons that you would like to analyze, for the classical magnetrons, you will use the thermionic emission. For the relativistic magnetrons, you will use the explosive emission. So let's have a look now how it behaves and how it needs to be set up correctly to reach the oscillation regime. First of all, let's consider the external static B field. You have here the permanent magnets, and you have here the z-axis, and you need here to calculate the static B field. You can extract the static B field directly from this figure. So you have here the field along the line, and then you have here the maximum B field, which then can be computed, which validate also your external signals. You need also to adjust the so-called magnetic insulation. So that means that you can do here a tracking analysis in order to compute and to validate the potentials that you have applied here and the magnetic field, which is perpendicular to the screen, in order to have a rotating E fields here in between the cathode and the anode structures, to have these magnetic insulations which will participate to induce the electromagnetic fields into the RF structures to create the microwave oscillation. Then you can also do the RF analysis. Here you can use the eigenmode solver. And there exists, you see here, a resonant pi mode where the phase shift of the electric field is 180 degrees between two vanes. The vanes is these cavities that you have around. You see here the electric field, which is then here defined with a phase shift of 180 degrees between two vanes. And since the particles are also moving around, then we have here some energies which then can be transferred from the electron beam to the RF structure. You can nicely see here the E field pattern and the evidence of the pi mode configurations at the resonant frequency of 2.45 gigahertz. We put some straps in order to make this mode unique and to prevent any mode competition, because if you have mode competition, of course, you will directly reduce the output power at the end. So there is just one mode which is considered for the interaction process. And then you see the magnetron oscillation occurs when a bunching effect of the electrons is generated. Then we have the so-called spokes formation. This is what you have here. And here 10 cavities lead to 5 spokes formation, and you can also extract from a fast Fourier transform here directly the output signal. And here you see the output results at 2.45 gigahertz. And then you have here the 4 kilowatt signals. And then you can also nicely see how we can extract here the microwave output signal. Let's now continue and finish with high power microwaves. This is an example, which is a backward wave oscillator. You have here the dimension of the backward wave oscillators, and this is the tapered slow wave structures that we considered. The beam energy is 600 keV with a maximum currents introduced, which is 5 kiloamps. And then we have a static magnetic field, which is also applied along the tube. Here you see you have also the information about the numerical settings, and this has been also reproduced from the paper that you have here. We can, in the same way, calculate here the output power, and then you see that we have a bunching effect which occurs. And here, this is a backward wave oscillator because you see that we have at 9.57 gigahertz, we have part of the signals which is moving backward. That's why it's a backward wave oscillators, but you have a cutoff frequency, which then allows these microwave signals being radiated forward. You have here the TM01 mode of extractions, and here you see that we have the output signals that we can also compute, and then we can calculate the backward wave oscillation efficiency, which is here 18% at 9.57 gigahertz. In terms of performance, this is also very nice. You can see that we have roughly 1 million of particles, and with the GPU compared to the CPU, we can here still have a speed factor of 7.5 for the whole simulation. And then, to finish with this presentation, I would like to speak a little bit about numerical dispersions and numerical noise. Here, high power microwave suffers about numerical noise. And this is something known for peak codes. And you have a maximum dispersions along the tubes, whereas this is minimized as soon as you are computing things in the diagonals of the mesh grid. So this is critical for these two examples that you've seen, but not that much for the magnetrons, where here you have an arbitrary movement of the particles, which creates no problems. You can reduce this by refining the mesh or introducing losses to damp the numerical noise. But this is also sometimes not that enough. So that means that, for instance, here, you see that at above 75 gigahertz, you have here the numerical phase velocity, and you can see that in this area, the particle beams is moving slightly faster than the phase of the electromagnetic waves. That means that you have a kind of a numerical Cherenkov effect. And if you place some probes into the tubes, then you can see where this numerical dispersions occurs and where you have these growing signals which occurs. And here you can damp the numerical noise by applying a special dispersions, which is available in our tools, in order to really have the main operating principles which occurs here at the operating frequency of the backward wave oscillator. So as a conclusion, you see that we have a complete technology with a different set of solvers, which then can be used and coupled all together to perform the whole design. And the multi-physics coupling is also possible if you would like to use also any thermal analysis in this context. Many devices transverse to several industries, and you can also design right first time through virtual prototyping. And this is something here really important to understand, that, and I like to mention here Professor Shamiloglu, which is really the reference in this domain, that no metal will be cut until simulations has demonstrated optimal performance. And the simulation is key here to really optimize the device that you would like to build at the end. Thanks for your attention. It's ready for the questions.